I'm asked how many molecules of ammonia gas are found in a certain volume of that gas at STP. This is not a balanced equation. There's no ratio between ammonia and itself. So I can simply relate them by an equation of number of particles over Avogadro's number, which is number of moles, is equal to volume over molar volume, which is also equal to number of moles. If I then want just the number of particles, I rearrange that, first putting in the volume, 34,05, then bringing the number, Avogadro's number, into the numerator over there. And so I get 6,022 times 10 to the power of 23. And finally divide by the molar gas volume, which is 22,4 decimeters cubed per mole. And I then get an answer of 9,15 times 10 to the 23 molecules. Now my number of molecules, when I have to relate that to a number of atoms, all I do is I write ammonia is NH3. For every one ammonia, how many atoms are inside that one ammonia molecule? So that's a unit, one ammonia molecule. There is 1 nitrogen and 3 hydrogens, which means that there are 4 atoms. But I don't have one molecule of ammonia. I have 9,15 times 10 to the 23 molecules. So I need to say, what did I do to the number 1 to make it into the number 4? I multiplied it by 4, so I'm going to take 9,15 times 10 to the 23 multiplied by 4, and I land up with 3,66 times 10 to the 24 atoms. How did I do that? I multiplied by 4. If I'm now asked to calculate the mass of sodium hydroxide needed to prepare a certain volume of a certain concentration, the first thing is that I don't know enough information, because if I look, my mass is equal to number of moles times molar mass. I don't have the number of moles. I can work out the molar mass easily enough, and we might as well do that quickly now. So if it's sodium, valency 1 because it's in group 1, hydroxide, valency 1 because I've learnt that it has a -1 charge. So the formula for sodium hydroxide is NaOH, and the molar mass of sodium hydroxide is therefore going to be equal to 23 plus 16 plus 1, which turns out to be 40 grams per mole. That's fine, but I still don't know my number of moles. So somehow I need to work out number of moles. And fortunately, I have got quite a bit of information. Number of moles is equal to concentration times by volume. So the concentration is given to me, 0,15, no problem. The volume, I have a bit of a problem because the concentration is per decimeter cubed and my volume is in centimeters cubed. Those need to become compatible units. So I need to convert centimeters cubed into decimeters cubed. How am I going to do that? I'm going to divide by 1,000. So it becomes 0,25. Multiply those two numbers together and you get 0,0375 moles. Now I have a number of moles, so I can substitute in 0,0375, and I've got a molar mass. I can substitute in 40, and I land up with a mass of 1,5 grams of sodium hydroxide. Looking at number 13, I have a solution of sodium carbonate. They've already given me a concentration of that solution. They asked me what mass of sodium carbonate is present in a certain volume of that solution. So let's try and do that first. So again, I'm going to get the number of moles first using the concentration and the volume. So number of moles is equal to concentration times volume. They've given me a concentration of 0,02 moles per cubic decimeter. And again, I need to convert this the centimeters cubed into decimeters cubed by dividing by 1,000. So it becomes 0,05 decimeters cubed. And then I get 1 times 10 to the -3 moles, or 0,001 moles. I then need to work out my mass. Mass is equal to number of moles times molar mass. I've got a number of moles, 1 times 10 to the negative 3. And my molar mass is of sodium carbonate. Really nice this time. They've given me the formula of sodium carbonate, so I don't have to work it out. So it's going to be 23 plus 23 plus 12 plus 16 plus 16 plus 16. And that works out to be 106. So 106. And I multiply that out and I get 0,106 grams of sodium carbonate. Then they ask me to write an equation to represent the dissolution of sodium carbonate. Well, I know what sodium carbonate is. It's Na2CO3, they told me, and it's a solid. I put it into water because that's how it's going to dissolution-ish, and I land up getting Na plus ions and CO3 2 minus ions. In each case, it's appropriate to write my phases as subscripts. I write aqueous, aqueous. This is not right. Inside every single sodium carbonate, there are actually 2 sodium ions bound to 1 carbonate ion. So I now need to put a 2 in front over there. I have now got a number of moles of sodium carbonate, or rather a concentration of sodium carbonate. They've told it to me, 0,02 moles per cubic decimeter. And therefore what we're going to do is unpack a mole ratio over here. So if I had a concentration of 0,02, and it's moles per cubic decimeter, let's pretend we are in a decimeter cubed of water. I have 0,02 moles of sodium carbonate, invisible 1 in front. I have exactly the same, because it's a 1-to-1 ratio, of the carbonate ion. But the sodium ion, I have double the number, so it's 0,04 moles in 1 decimeter cubed. So they are going to now give me a concentration of sodium ions, and when I use the square bracket, I'm just shorthanding for concentration of. Concentration of sodium ions, 0,04 moles per cubic decimeter. And it was just ratios that got me to this. And when I'm looking at the carbonate, it's going to be a square bracket again, CO3 2 minus is equal to 0,02 moles per cubic decimeter.